So, in the last lecture, you have seen the complex form of the Fourier series. Now, from this lecture, effectively we are going to start the another transform, which we call as the Fourier transform. This, if you remember, in Laplace transform, basically the interval of the function was from 0 to infinity. But in physical problems, always it may not be possible that the parameter lies in the interval 0 to infinity, but it may lie in the interval from minus infinity to plus infinity. So, how to handle the situations where one function is defined in minus infinity to infinity and we want to find out a solution. For that, basically the Fourier transform was developed. I will come to that, but initially let us start with the Fourier integral representation of a function. So, just see, whenever Fourier integral representation, you have seen that we can define a function in the interval minus L to L. Now, when L approaches infinity in a Fourier series, then this leads to introduction of a different type of representation, which we call as Fourier integral representation or FIR, where the function f x is defined for all x and need not be periodic. Please note this one. The function is defined for all x whenever L approaches infinity and it need not be periodic in that case. This representation forms the basis of an integral transform, which we call as Fourier transform, that is similar to your Laplace transform, but only note that in Laplace transform the variable, the function f x is defined in 0 to infinity, but here the function is defined from minus infinity to infinity, because in real life in many situations a function will be defined in minus infinity to infinity. So, let us see what happens in this case. We have a function f x, which is defined in the interval minus infinity to infinity, and this is a term by term integrable. That is, there exists an integral such that we can write down this thing minus infinity to infinity mod of f x dx. This is equals, we will get a finite value. So, let us see, this one is minus infinity to infinity mod of f x dx. This is equals to say q. As I was telling you, this is equals to q, say this is equals to 1, that is the integration. If I evaluate the integral, it has a definite value. Further, suppose the function f x can be expanded in terms of Fourier series in the interval minus infinity minus L to L. If the function f x can be expanded in Fourier series in the interval minus L to L, then you can write down f x equals from the Fourier series a 0 by 2 plus summation n equals 1 to infinity a n cos n pi x by L, a n cos n pi x by L plus summation n equals 1 to infinity b n sin of n pi by L into x. So, this is your equation 2, where you know your a naught is equals to 1 by L minus L to L f t dt, your a n is 1 by L minus L to L f t into cos of, this will be n pi by L into t dt, and your b n similarly is 1 by L minus L by minus L to L f t into sin of n pi by L into t into dt. So, if I put the values of these coefficients a naught, a n and b n in the equation 2, that means I am now representing this f x in terms of integrals by substituting the values of the coefficients a naught, a n and b n in equation 2, then I can write down f x equals 1 by twice L minus L to L f t dt plus 1 by L summation n equals 1 to infinity minus L to L f t into cos of n pi by L into t dt into, I have to put this thing dt into your cos n pi by L into x plus 1 by L summation n equals 1 to infinity minus L to L f t into sin of n pi by L into t dt into sin of n pi x n pi L n pi divided by L into x into dx. This will come into dx because the dx will not come here, dt is here. So, once I am getting this, now these values cos n pi L by t into cos n pi L by x, this we can expand and this thing we can write down again f x equals 1 by twice L minus L to L f t dt, this will remain as it is, plus 1 by L summation n equals 1 to infinity minus L to L, your f t can come here into, I can combine this, that is cos n pi by L t into cos of n pi by L x plus sin of n pi by L into t into sin of n pi by L into x whole into whole into dt. I am integrating with respect to t. So, this equals 1 by 2 L minus L to L f t dt will come plus 1 by L summation n equals 1 to infinity. F t is here and this cos A cos B plus sin A sin B, this I can write it as cos of n pi into t minus x by L into dt. Summation will come, so that here your integration will also come from minus L to L f t into cos of n pi into t minus x by L into dt. So, effectively what we are doing now, this is say equation 3 we are putting, this as equation 3 we are giving. So, this cos n pi t by L into cos n pi x by L and this plus sin n pi t by L into sin n pi x by L, these two we are putting over here. Now, what actually we want to investigate what will be the form of the expression 3 whenever L approaches infinity. Whenever L approaches infinity, what will be the form of this equation 3? We want to investigate that now. Let us introduce some new notations. Say alpha 1 equals pi by L, alpha 2 equals 2 pi by L. Like this way, alpha n equals n pi by L, we can write down, and alpha n plus 1 similarly will be n plus 1 into pi divided by L, n plus 1 into pi by L. So, that you can write down alpha n plus 1 minus alpha n, this is equals pi by L, or that is you can write down del of alpha n is nothing but pi by L, and so this is equation 4. So, we are obtaining using these notations alpha 1 equals pi by L, alpha 2 equals 2 pi by L. Like this way, alpha n equals n pi by L and alpha n plus 1 equals n plus 1 to pi by L. You can tell alpha n plus 1 minus alpha n, which is nothing but the delta increment, which I am writing del alpha n, this is equals pi by L. Now, substitute this value from 4 into equation 3. If you put it into the equation 3, then you will obtain 1 by twice L minus L to L f t dt, it will remain as it is, plus 1 by pi minus n equals 1 to infinity summation n equals 1 to infinity minus L to L f t into the earlier term, that cos of a t minus x into cos of n pi into t minus x by L, that can be replaced as cos of alpha n into t minus x into dt into del alpha n. If I substitute this, here you note that the earlier term was cos of n pi into t minus x by L. This we are replacing over here by this substitution, and therefore, this will become cos of alpha n into t minus x, and this will be replaced here as del of alpha n, which will come. So, whenever L approaches infinity, what will happen? If L approaches infinity, the first term here, if you see, this approaches 0. Why this approaches 0? I am saying because say if you take absolute value 1 by twice L minus L to L f t dt, this you can write down, this is less than equals 1 by twice L minus L to L, this mod you can bring inside the function mod of f t into dt, which is again less than, you can tell 1 by twice L minus infinity to infinity. Whenever L is approaches infinity, modulus of f t dt, and we know that this quantity has a finite value and the finite value is q only. So, it becomes 1 by twice L into q, and this approaches 0 whenever L approaches infinity. So, if you fix L, what will happen? If you fix L, the expression in the parenthesis, whatever we are writing for the function alpha n, which this takes the value from pi by L to infinity. So, for a fixed L, this alpha n takes the value varies from pi by L to infinity. So, at first we are showing that the first term of the equation, original equation, then it is becoming 0, and then as L approaches infinity, as L approaches infinity here, L approaches infinity, then your f x now will become 1 by pi, then it is 0 to your equation 5. If you see your in equation 5, which was f x equals 1 by twice L minus t to t f t into dt, which is 0, and 1 by pi summation n equals 1 to infinity, that will be from 0 to infinity and minus infinity to infinity f t into cos of alpha into t minus x dx dt into d alpha, del of alpha n will be replaced by d of alpha, and this is your form, and this is say the equation 6. So, f x as L approaches infinity, we are writing f x equals 1 by pi 0 to infinity minus infinity to infinity f t into cos of alpha into t minus x dt into d alpha, and this expression is known as the Fourier integral representation of the function f x. So, as L approaches infinity, that integral equation 5 will be transformed to f x equals 1 by pi 0 to infinity minus infinity to infinity f t into cos of alpha into t minus x dt into d alpha. This we call Fourier integral representation of the function f x. Now, this equation 6 occurs at all points, means at all points when the function is continuous. If the function f x is continuous at all points of x, then I can find the value of f x at any point by using the equation 6. Suppose at a point the function is discontinuous, at a particular point the function is discontinuous. So, again by observing the concept what we have told in the Fourier series, you can write down the value of this integral in that case will become 0 to infinity minus infinity to infinity f t into cos of alpha into t minus x into dt into d alpha. This value in that case, if f x is not continuous at a point, then I have to take the average of left hand limit and right hand limit, which we have done earlier also for the case of Fourier series, that is f of x plus 0 plus f of x minus 0 by 2. So, please note that if f x is continuous at a particular point, then the value Fourier integral representation I can write down f x equals 1 by pi 0 to infinity minus infinity to infinity f t into cos of alpha into t minus x dt d alpha. If at a point x the function is discontinuous, is not continuous, then the value of integral will not be f x, but it will be f of x plus 0 plus f of x minus 0 divided by 2. So, please note this thing, and let us just quickly see whatever we have told now. Your function is given, the function is defined in the infinite interval and absolutely integrable. That means, it has a, whenever I will integrate the absolute value of f x in minus infinity to infinity, I will obtain a definite value, say it is q, and further the function f x is such that it is expandable in Fourier series. So, that I can write down the Fourier series expression of 2, where a naught, a n and b n are given, which we have derived earlier. We know it from the Fourier series itself. You can understand now that before starting Fourier transform, why we have done Fourier series, because unless we do the Fourier series, these terms will not be known to us and we have to derive the entire thing. So, in the Fourier series, a naught, a n and b n are this. We substitute the values of a n and b n in the given Fourier series. So, you will obtain this, and I can make the cos terms and sin terms together. So, that the terms cos n pi t by l into cos n pi x by l plus sin of that function into sin of n pi x by l, that I can write it in terms of cos of n pi into t minus x by l into dt. Now, as t approaches infinity, as in this equation, as l approaches infinity, what happens to the integral, that we want to check. Therefore, we are introducing a new notations alpha 1, alpha 2 like this way, alpha n. So, that alpha n plus 1 minus alpha n, that is del alpha n equals pi by l. If you substitute it, I can write it in this particular form, minus l to l, this one. So, you just see the difference here. It was f t cos n pi t minus x by l into dt, and this has been changed to, after substitution, f t into alpha n into t minus x. I am replacing alpha n is equal to n pi by l, that value I am replacing, and for that reason into this difference will come, that is pi by l, I am writing as delta into alpha n. So, here delta into alpha n is coming because pi by l I am putting here, and pi by l is nothing but alpha n plus 1 minus alpha n. So, using this, as l approaches the 0, the first term of the right hand side, that is this first integral, will be 0, 1 by twice l minus l to l f t dt, this will approach 0. How? Let us see. Absolute value of 1 by twice L minus L to L f t dt less than equals 1 by twice L minus L to L modulus of f t, modulus I can bring on f t, and this again 1 by twice L minus less than, it was minus L to L, and this value obviously will be less than minus infinity to infinity as L approaches 0, and this has a finite value, the integral, that is q. So, I am getting q by twice L. So, whenever L approaches infinity, the first term will approach 0. Now, for any fixed L, for the expression of the parenthesis is a function of alpha n, and which will vary from pi by L to infinity. So, as L approaches infinity, this now I can write down f x equals 1 by pi 0 to infinity minus infinity to infinity f t cos of alpha n will be replaced by alpha into t minus x dt, and del alpha will be replaced by d alpha, and this is known as the Fourier integral representation of the function f x. Now, this equation 6 occurs at all points where the function is continuous, or in other sense, if the function is continuous, the value of the function will be that integral. The question is, if the function is not continuous at that point, what will be this integral? As we have seen in the Fourier series case, this value is nothing but, in that case it will be f of x plus 0 plus f of x minus 0, f of x plus 0 plus f of x minus 0 divided by 2, when the function is not continuous at the point x, then the value will be this one. Now, let us expand the integral in the given equation, this cos of alpha into t minus x, means we want to further investigate this equation 6. So, we will expand this cos of alpha into t minus x. So, if we expand this cos of alpha into t minus x, this you can write down cos of alpha t into cos of alpha x plus sin of alpha t into sin of alpha x. And if I put this value in the earlier equation 6, the equation which I showed just now, then you can write down f x equals 1 by pi 0 to infinity minus infinity to infinity f t into cos of alpha t dt into cos of alpha x d alpha, plus the second term will be 1 by pi 0 to infinity minus infinity to infinity f t into sin of alpha t dt, this is one term, into sin of alpha x into d alpha, and say this equation is number 7. So, please note this equation 7, f x equals 1 by pi 0 to infinity minus infinity to infinity f t into cos of alpha t dt into cos of alpha x d alpha, plus 1 by pi 0 to infinity minus infinity to infinity f t into sin alpha t dt into sin alpha x d alpha. Let us take some particular cases of this equation 7, means when if the function f x takes different forms, what will happen to this equation. So, please note this equation 7. On this we want to consider some special cases. Case number 1, you can tell that your f x is even. Whenever your f x is even, therefore, your f t cos of alpha t, this is even, and your f t into sin alpha t, this is odd. So, whenever I have the even and odd function, I know the properties, that is minus infinity to infinity f t into cos of alpha t dt, this is equals to 2 into 0 to infinity f t into cos of alpha t dt, and also we know it minus infinity to infinity f t into sin alpha t dt, this is equals to 0. So, in that case, if I substitute these two things, equation 7, let me write later, equation 7 will take this form, then equation 7 can be written in that case f x equals, simply you will obtain 2 by pi 0 to infinity f of t into cos of alpha t dt into cos of alpha x d alpha. Say this is equation 8, and note that your function, we have assumed that f x is even now. Your function f x is even. Then using those definite integral values, you are writing f x equals 2 by pi 0 to infinity f t cos of alpha t dt into cos of alpha x d alpha. Similarly, for case 2, now say f x is odd function. On the proceeding on the same way, whenever f x is odd function, then using the properties of definite integral, your f x will be equals to 2 by pi 0 to infinity, it will be f t into sin alpha t, sin of alpha t dt into sin of alpha x d alpha. So, it is equation 9, earlier one was equation 8 for if the function f x is even. So, if f x is even, then f x can be represented by the integral of equation 8. If f x is odd, then f x can be represented by equation 9. And again please note that in for both the equation 8 and 9, if at a particular point x the function f x is not continuous, that is discontinuous, then the value of f x will be equals to simply f of x plus 0 plus f of x minus 0 by 2. So, please note this one, when f x is not continuous at a point x, then we say that it is f of x plus 0 plus f of x minus 0 divided by 2. So, let us stop here. We will do the other part in the next lecture.